this video, we are going to determine an equation of a polynomial two different ways. First from a graph, and then second from a data table. What we want to do in this first example then is determine an equation that models the following graph. The first step that you want to do when you're finding the equation of a polynomial from a graph is you want to find the x-intercepts and then find their respective orders. If we take a look at our graph, then we have an x-intercept at 1, we have another one at -1, and we have our last one at -2. If we were to write those as factors, the first one would be x minus 1, our second one would be x plus 1, and our last one would be x plus 2. These two here cross the graph. Their order is just going to be 1. This one here, our x minus 1, touches the graph but doesn't cross the graph, meaning that it's going to be an even number of times. We would have to put the squared here to indicate that. We now want to find the leading coefficient a by plugging in any point on the graph except for an x-intercept. Let's set up the general equation for our graph then. It's going to be f at x is equal to our leading coefficient times each of our factors, x plus 2, x plus 1, and x minus 1 squared. If we were to plug in an x-intercept, that would set one of our factors equal to 0. So 0 times a, it's just going to give us 0. It's not going to give us what our a value is. So we do need to pick a different point on the graph other than an x-intercept. Let's choose this point here, -1/2 and 3/2. You can pick any point as long as it's something that's easy to sub in, easy to pick, easy to find. Those are your best choices. Subbing this in then, we'd have 3/2 is equal to a times -1/2 plus 2, -1/2 plus 1, and -1/2 minus 1 all squared. Simplifying, we would have 3/2 times 1/2 times -3/2 all squared. Since these appear on both sides, we can cancel those out. 1 then equals a times 1/2 times 9/4. 1 then equals a times 9/8, meaning that a is equal to 8/9. That means that our equation then for this curve is f at x is equal to 8/9 times x plus 2, x plus 1, and x minus 1 all squared. Use the degree and the sign of the leading coefficients as a check. So we know looking at our graph, we should be an even degree function because our end behaviors indicate that, and we know that it should be a positive leading coefficient because both of these are pointing up. So if we check that here, our leading coefficient is positive, and if we find our degree is 4. To determine the equation of a polynomial function from a data set, we need to use finite differences. Finite differences, just as a refresher, for a polynomial function of degree n, where n is a positive integer, the nth differences are going to be equal or constant, they're going to have the same sign as the leading coefficient, and they're going to be equal to this formula here, which I'm going to show you below how to use. In our example then, we have several data points. So what we need to do first is determine the finite differences. We're going to plug these values into our data table then. We've got -3, -68, -2, -27, -1, -10, 0, -5, 1, 0, and 2, and 17. To find the first differences, we need to take the second y value, which is -27, and subtract the first y value, which is -68. If we do that, we get
41. We'll continue doing that for each of these sets then. The next one would be negative 10 minus negative 27. It's going to give us 17. Then we're going to have 5, 5, and 17. Taking a look at the first differences then, they are not constant. We're going to have to now take the second differences. Like the last ones, we're going to do the same thing. We're going to take 17 minus 41, so it's going to give us negative 24. Keep working our way down here. We'd have negative 12. 5 minus 5 is going to give us 0. And the last one would give us positive 12. Again, still not constant, so we need to find the third differences. If we do that, negative 12 minus negative 24 gives us 12. 0 minus negative 12 gives us 12. And 12 minus 0 gives us 12. The third differences are constant then. That then means that our degree is going to be 3 because our third differences are constant. To find the leading coefficient, A, we're going to use the equation given up here, this one here. Now the way we want to set it up is n is our nth differences, so in this example, n is going to be equal to 3. So it says that our third differences are going to be equal to this equation here. Setting that up then, our third differences are equal to 12, and that's going to equal to a times, putting in n would be 3 times 2 times 1. If our fourth differences were constant, then this part of the equation would be 4 times 3 times 2 times 1. Now to find the leading coefficient, we are just going to solve this equation. So 12 is equal to 6a, meaning that a is going to be equal to 2. Now unfortunately this is where it's going to start getting more complicated. We're going to set up the general equation for our function. With a degree of 3, we know we've got a leading constant with an x to the third, plus our next term would be our bx squared plus cx plus d. We now need to find the value of our 4 variables a, b, c, and d. We know a is our leading coefficient, so that's equal to 2. We've already got that one. We don't know what b is, or c, or d. The way that we're going to do this then is we're going to plug in different points from our data table in order to solve for the unknown coefficients. A really good place to start is to sub in the easy points. And by easy points, I mean if you're given, say for example, an x-intercept or a y-intercept, those are going to be easy points. Let's start with then the point 1 and 0. This would be an intercept. If we plug that into our general equation, y is 0 is equal to a times x cubed, so that's going to be 1 cubed plus b times 1 squared plus c times 1 plus d. We know that a is 2, so we can sub in the 2 there. We're going to have 0 is equal to 2 times 1 cubed is just going to be 2, plus b times 1 squared is just b, plus c times 1 is just c, plus d. Can't really do much else with this equation now, but we'll keep this one in mind because we're going to come back to it later. A second easy point would be our other intercept, which was 0 and negative 5. Plugging that in, y is equal to negative 5 is equal to a times 0 cubed plus b times 0 squared plus c times 0 plus d. So this is a really nice equation because anything times 0 is just 0. This will be 0, this will be 0, this will be 0. We are left with just d. That means now that we know what the value of d is. It's negative 5. Coming back up to our table then, let's plug that in. We know that is now negative 5. We still need to find b and c. Trying another point then, let's sub in the point negative 1 and negative 10. Y is negative 10 is equal to a times negative 1 cubed plus b times negative 1 squared plus c times negative 1 plus d. We know what a and d are, so we could sub in those values. We're going to have 2 times negative 1 cubed is just negative 1, plus b times negative 1 squared is just going to be b, c times negative 1 is minus c, and then d is negative 5. Let's simplify this a bit. So negative 10 is negative 2 plus b minus c minus 5. If we bring all of our numbers onto one side, we'd have negative 10 plus 2 plus 5 is equal to b minus c. That is going to give us negative 3 is equal to b minus c. You could rewrite that too if you don't like the negatives here. We could say 3, if we multiply both sides by negative 1, is equal to negative b plus c, or if you rewrite that, that's c minus b. We still don't know what c and b are though, but we can take a couple of our equations and sub in some values. So if we go back to that first one that we had, that was 0 is equal to 2 plus b plus c plus d. And we sub in our value for d because we know it's negative 5. And we're going to have 2 plus b plus c minus 5. Simplifying this, let's bring all of our numbers over onto one side. 3 is equal to b plus c. We now have two equations, two unknowns. We can solve for either b or c. Let's then use substitution, and if we do that, you'll notice they're both equal to 3, so we could set these two equations equal to each other. That means that b plus c is equal to c minus b. Rearranging then, if we bring the b over here, we'd have 2b plus c is equal to c. Rearrange a little bit more. If we bring the c over, then 2b is going to be equal to 0. So b also equals 0. Finally, we've got b, so now we can find c. We can sub that back into this equation here. So we're going to sub b equals 0 into 3 equals b plus c. So 3 equals 0 plus c, meaning that c is going to be equal to 3. That means then that our equation, we could plug in back all of our a, b, c, and d values, is going to be equal to a, which is 2x cubed, plus b, which was 0x squared, plus c, which is 3x, plus d, which was minus 5. We probably don't want to include this term, so let's just rewrite this as f at x is equal to 2x cubed plus 3x minus 5.